Let's start this talk. So my name is Yu Tao. I'm a data scientist at the EMC. So within the company, we're leveraging the big data and the machine learning to improve the management and orchestration intelligence of cloud infrastructure and data center, as well as conduct open solution innovations for different industry verticals. And externally, we provide a big data solution consulting services to customers, especially in the Asia Pacific region. So today, this talk is about how the Spark ecosystem facilitates the online security analytics on larger scale video surveillance systems, which is an solution innovation initiative being carried out at EMC. So video surveillance is critical to public security, right? So here are three real customer cases of security analytics that are coming from the famous coffee chain store company. And you can see that these three use cases are actually beyond what traditional video surveillance means, right? So you can see that here it involves a correlation of video data and non-video data, and it requires different levels of analytics latencies, and it accesses a huge amount of video data or multiple video streams, right? So what are the challenges for security video analytics in the big and the faster data area? So there are several. The first one is faster data injection, right? How to collect the video data from heterogeneous sources and feed them into the analytics pipeline as soon as the data generated. And the second one is scalable data storage, how to archive a huge amount of raw video data and derive the metadata and store them as much and as persistent as possible to facilitate the non-real-time analytics use cases. And the third one is about the multi-latency analytics, real-time, interactive, ad hoc, and offline. And the fourth one is about cloud integration, because now we are living with cloud computing, so it will be the video surveillance and the analytics. And the final one is about the management orchestrations, how to make these functionalities about seamlessly work together within one system or solution. So, so at EMC, we're trying to, we're spending tremendous efforts on resolving these challenges of modern video analytics, and the deliverables is an innovative solution which we call Video Analytics Data Lake, VADL, VADL. So in VADL, we use Spark quite a lot. We use Spark streaming for online video processing and detection. We use Spark Core and SQL for the ad hoc video content search. And we use Spark machine learning libraries for offline video analytics and model training. And recently, we started to try out the various deep learning on Spark frameworks to run our deep learning image processing algorithms. And so the first thing we're to do is to enable Spark to process the raw video data. So we're faced with two issues. The first one is that the Spark doesn't come with the native video processing capabilities. And the second one is about due to the performance considerations that most of the existing video processing libraries like OpenCV, they are written in C++. So here the issue is that we want to leverage this rich set of legacy C++ code because we don't want to reinvent the wheels. So we have to find ways of letting this C++ code to seamlessly work together with within the Spark programs, which may be in Scala or Java, right? So our solution here is the pipeline operator of a Spark, which will take an RDD as input and then pass the RDD data to an external command or program, and then for execution, and then return the execution results as a new RDD with a type of PipedRDD. So as we will see that this PipedRDD operator will becomes the knob of where we can execute our C++ video processing code. So, so there are several common video processing functionalities which will step-by-step convert the unstructured video data into structured and meaningful video information that can be immediately leveraged by analytics use cases. So these functions including the video transcoding, the background extraction, the object detection, feature extraction, etc. And their implementations are all included in a well-known computer vision libraries like OpenCV. And in VADL, we're also developing our own algorithms and implementations using new techniques like deep learning. So come back to the problem for Spark to process raw video data. So the solution is simple and effective. So what we do is we just encapsulate the video processing functions into external programs written in C++, and then we pipeline these functions by utilizing the PipedRDD in Spark jobs. And look at the pursuit code, that's quite elegant, right? So in VADL, we constructed a video injection system where we collect the video data from heterogeneous sources like online cameras and video records, and then feed this video data and derive the video information into different destinations of storage, analytics, and the front-end display. So this system has 3 key system components. The first one is the injector as adapted to different data sources, and the process as for relevant computation, and the ingester as for sending the video data to different destinations. So here we leverage Spark streaming to implement the process component and to conduct the video processing during injection. So here the purpose of video processing, online video processing during injection are twofold. The first one, on the one hand, their real-time analytics use cases takes place here for extremely low latency, like anomaly detection. And on the other hand, for those interactive and offline analytics use cases, they may need information such as they may need those well structured and well formatted and structured information such as the object and metadata, the object itself, and the object features which will be computed on the fly during the injection and before the storage, right? So, here, during the online video processing, the Spark streaming will conduct several tasks such as object detection, feature extraction, classification, recognition, indexing, something like that. And optionally, we put in Kafka in front of a Spark to stage the data pipeline from the collectors and to ensure the correctness of the processing results. And here, the Spark streaming may also leverage the machine learning and deep learning models that are incrementally and continuously refreshed by the underlying deep learning systems. So here are some implementation details. So basically, the receiver will read the video data in a certain timestamp, and then encapsulate the data into RDDs and put these RDDs into an RDD queue. And in the meantime, the driver will create a D string out of this RDD queue and then process the D string data as a micro RDDs in a separate timestamp, right? So, and here, in one Spark streaming job, it can handle one or multiple video streams. So video content search is a very important feature of VADL. So here it has 2 forms. The first one is content-based video object search, which will look for the objects within a video frames that are similar to a given object, most likely as an image. And furthermore, the search result could be filtered out based on conditions on the object metadata, for example, where this object is detected and by which camera it is detected, right? And the second form is the semantic-based video object search, which is more complicated and advanced. And here the video schemas that it looks for are usually queried with semantic texture descriptions. So here I want to briefly introduce how we use Spark in the first content-based video object search scenario. So here is the overall architecture of the video content search engine. So the input query here is an image which contains a target object. And the first thing to do is to extract the target object's features and then invoke the Spark to look at the video storage and then search for the top K similar objects that are most similar to the targeted object, and as well as satisfy the filtering conditions on the object metadata. And then all the relevant metadata information will be retrieved from of these top K similar objects that were retrieved from HBase and returned to the user. So here, in the video storage systems, the HBase will store all the relevant video information like metadata and something like that that will be derived from the online video processing during injection. And the raw video data will be stored in the HDFS. And in addition to accelerate the top K search, we will build indexes on the object features and the metadata, and store the indexes along with a part of the object features in HDFS. So in other words, during the top K search, the Spark will the Spark will process the index and features in HDFS. So when we talk about the similarity of the features, similarity of the video objects, actually we are talking about the similarity of the features of the objects, right? So here, the similarity of the features are measured according to certain similarity score functions based on some similarity measurement method like cosine distance. So here, there are numerous features for consideration, including the color, the texture, the shape, the saved feature set, and those less human-readable deep learning features. So, so in VADL, when we from the perspective, from the system engineering perspective, when we measure the similarity of 3D objects, taking into account too many object features will result in two main issues. The first one is a performance bottleneck because the similarity calculation complexity will grow exponentially along with the number of the features. And the second one is about will be very hard to assign appropriate weight to each feature in the similarity score functions, and therefore it will affect the accuracy of the similarity scores. So we need to balance the efficiency and the accuracy of we need to balance the efficiency and accuracy of the similarity calculation by selecting only subset of the key features for the similarity calculation. So here, in VADL, we utilize the principal component analysis algorithms, which is available in MLlib, and it is distributed version for the feature dimensionality reduction. And furthermore, in order to further improve the top K search performance, here we also build the locality sensitive hashing index on the object features, which will pre-cluster the similar objects into buckets, and then so that we can route the target object into the corresponding bucket without computing certain objects at runtime. So here is the Spark top K query pipeline. So for each work, it will look at the subset of candidate objects that are filled out by the index, indexes on object features and the metadata, and then it will calculate the similarity score between each candidate object and the targeted object, and then they will order all these similarity scores and then send the local top K objects to the driver. And after receiving all the local top K objects from each worker, the driver will be able to identify the global top K objects that are most similar to the given target object. right? So here is the corresponding Scala code example. So where the order and the top K operator has been encapsulated into the take all data function implementation details, right? So in VADL, we are interested in deep learning because it can be used for multiple tasks like feature extraction, classifications, suspect detection, and recognitions. So there are several native deep learning systems like Caffeine and TensorFlow. They're all good, they're all useful, and we're satisfied with their performance and functionalities. But here, one thing that we are looking to is to simplify the system components. We could set up a separate deep learning system cluster, but if we could reuse and share the existing system components, especially Spark, then things will become much simpler and better, right? So that's why we are now investigating various deep learning on Spark framework like DeepDisk and Deep Learning 4J. So frankly speaking, I haven't had much to share with this regard, but I hope I can do that during next summit. So good. So I'm finishing my talk today. Thank you so much. So hopefully you are not so hungry, so we can take some questions. Thank you.
So the scalable PCA you mentioned, was it the default one from MLlib, or you added something on top of that to make it distributed, or was the default distribution given by Spark?
So the principle is that when the dimension is small, like the SIFT feature set, we will use the original centralized version of the PCA. But when the dimension becomes so large, the complexity becomes exponentially, so we will use a distributed version. So the distributed version is not available in the MLlib implementations, but we do it by ourselves. Yeah.
I know you said you didn't have much experience on the deep learning side of it. Do you guys envision just using the deep learning aspects as a replacement for almost like a biometric algorithm where you're just trying to figure out when two of the same people were in the same frame, or are there other aspects that you hope to kind of glean from the deep learning side of this?
Yeah, we're doing this. Actually, we have two work streams in this project. We have the platform and infrastructure teams, so we're working on the overall scalable systems. And in the meantime, we'll also have another work stream to focus on the algorithms aspects to try to investigate how deep learning things can be deployed and utilized by the real production and the system environment. Yeah.
Did you use GPU?
So far, no. But that's a good question, because if we use a separate deep learning cluster, definitely we can use GPU, right? The Caffeine and TensorFlow, other frameworks, they all support the GPU. But the issue is that if we want to reuse the Spark, then we have to wait for Spark to support GPU officially, right? That's one thing that we're looking for. Yeah.
Any other questions? All right, if not, then let's give Yutal a big round of applause.
Yeah, thank you.